Okay, here's the recording in progress. So we'll share the screen. Okay, so we're getting actually very close to the end. Test we just had was on trig. Yes, it was more challenging, but you're supposed to know trig before you go to calculus. And let's see, I have given you the video for the solutions, and I should have emailed you back your particular exam score. So if you did not get it from me, let me know right away so I can get that to you. And the usual caveat, if you did not submit the homework, then that's why I didn't grade your exam. There's a homework requirement. I don't grade your exam if you don't submit the homework. So if you didn't get something back from me, maybe that was why. All right, so we have exam 5 and we have exam 6, and then we have a final exam, and that's going to be it for the course. The next exam covers very little material. It's on exponential and logarithm functions. Okay, so 1 in 19 odd, 35 and 37. And in fact, I have decided, I think, let me double check. Yeah, I'm going to skip this. How do you like that? So it's going to be 1 in 19 odd. And that's about it. Okay, and we have a short week this week. We have Veterans Day. We're celebrating Veterans Day on Friday. I know some people have Thursday off, but we don't. So that being the case, your quiz this week will be Thursday. Usual rules, submitted by 11:59, and then our holiday is on Friday. And there's another couple of days of holidays coming up for Thanksgiving. So this is when the holidays begin. And before you know it, we're all finished. Okay. All right, so I'll get started with 5.2. This chapter is not a long chapter. That means most days I'll finish fairly early. In which case, if you don't have any questions, you can just leave and we'll go from there. This should be mostly review also. You should have seen exponential and logarithm functions before, but we're just trying to brush up our skills with that so you can be ready for that when calculus comes. Okay. So chapter 5, exponential and logarithm functions, page 279. And there is a 5.1, but there are no homework problems in 5.1. You can look at it or not. So page 280, quick review of some properties of exponents that you've all seen before. A to the R1 plus R2, A to the R1, A to the R2. A to the R1 minus R2, A to the R1 divided by A to the R2. A to the R1 to the R2, you can multiply the powers, A to the R1 times R2. This is sort of like a distributive law here. A1R, A2R, you can factor it out as A1, A2 to the R power. Likewise for division, A1 to the R divided by A2 to the R, A1 divided by A2, all raised to the R power. Okay. So properties of exponents. Okay, now on page 281, we have the natural exponential function. Okay, so exponential functions look like this. F of x equals a to the x. A is a positive number. We usually don't let it be 1 because 1 to the x is always 1. That's kind of too boring. Okay, so a is any positive quantity. That's called the base. Okay, so a to the x power is an exponential function. So 2 to the x, 3 to the x, 10 to the x, 1/2 to the x, 1,000,000 to the x, pi to the x. Those are all exponential functions. You don't have to write any of that down. Okay, page 282. It's up to you if you want to put this on your cheat sheet or not. Exponential functions all tend to look like this. Okay, the base is bigger than 1. Here's 5/4 to the x, 7/4 to the x, 2 to the x, 3 to the x, 5 to the x. So they all go through 0, 1. So if you want to put this on your cheat sheet, you may. It does make sense that they all go through 0, 1 because whatever the base is, if I raise it to the 0 power, it's going to equal 1. Okay, and then on the right side of the y-axis, they seem to be increasing, going to infinity faster, right? 5/4 is smaller than 7/4, which is smaller than 2, which is smaller than 3, which is smaller than 5, right? And you can tell that just by plugging in 1. If I plug in 1, this is 5/4. This one is 7/4. This one's already 2. This one's already 3. This one's already 5. So it goes like this. But if you notice, to the left of the y-axis, they switch. The one that used to be in the bottom is now on top. So notice this red one, 5/4 to the x. It's on top. And then at 0, 1, now it's on the bottom. And likewise, I'm not sure if you can see this green one here. 5 to the x, it's kind of greenish. It's the highest one here. On this side, however, it's the lowest. And that's the way they all work. Okay, so after the point 0, 1, they switch. The ones in the bottom become on top, and so on. Okay, they all pass through 0, 1. Okay, so it looks like for all of these functions, a sub a to the x approaches 0 as x approaches negative infinity. If I go way out to the left, they all approach 0. What happens if I go way out to the right? They all approach infinity. They get bigger and bigger and bigger. Okay, now how about if a is between 0 and 1? It's a fraction smaller than 1. They all tend to look like this. They're decreasing. So here we go. 2/3 to the x, 1/2 to the x, 1/3 to the x, and so on. So if the base is smaller than 1, the graph is decreasing. You go like this. So in this case, when x goes to infinity, y approaches 0. And when x goes to negative infinity, y approaches infinity. Once again, they all pass through 0, 1. So I'm not sure if you can read all these, but that's 2/3 to the x, 1/2 to the x, 1/3 to the x. For all of them, if you plug in 0, you get 1. And then notice, let's see. Excuse me. For the yellow graph, 1/3 to the x is lowest. 1/3 is smaller than 1/2, which is smaller than 2/3. And then once again, on this side, they switch. Right? So the red one, which is on top here, was the lowest here. And likewise, the yellow one, which is above here, becomes the lowest here. So all these graphs, once they pass through 0, 1, they switch. The smallest becomes the largest, and the largest becomes the smallest, so to speak. Okay. All right. Then, of course, we know what to do with various functions. So here's a graph of 2 to the x. So something quick and dirty for exponential functions. If the base is bigger than 1, they pass through 0, 1, and they all kind of look sort of like that. And then what are we going to do? We're going to do our usual stuff, like subtract 3. That shoves the whole graph down 3 units. So this is 0, 1. This is 0, -2. The asymptote used to be the x-axis, which is y equals 0. If I move the whole graph down 3, the asymptote becomes y equals -3. And so on. Okay, domain and range of the exponential. Let's look at this. The domain, well, all real numbers. Go as far to the left as you want, far to the right you want. So the domain is negative infinity to infinity. I would just put the funny looking R. It says the same thing. You can do that also. You go forever to the left, go forever to the right. How about the range? The range is from 0 to infinity, not counting 0. Okay. And that will change if you move the graph up or down, of course. But just a regular exponential function, the range is basically positive quantities, positive numbers from 0 to infinity. Okay. And then, of course, we're going to stretch the graph. 2 to the x multiplied by 3, 3 times 2 to the x, so it shoots up quicker. We're going to move the graph to the left or right, it looks like. 3 times 2 to the x, 3 times 2 parentheses x minus 1. That takes the red graph, moves it over 1 unit to the right. So it looks like that.
This might be a silly question, but is 3 times 2x is same 3 times 2 to the power of x, the same thing as 6 to the power of x?
Is 3 times 2 to the x the same as 6 to the x? Good question. It is not, because by order of operations, this is an exponent. That's multiplication. So from our order of operations, PEMDAS and all that stuff, right? Exponent has precedence over.
So if we were to see 6 to the power of x, we couldn't like factor out that 3.
For 6 to the x, you should not factor out the 3. Right.
I see.
So this is a different function. This is 2 to the x times 3. And if you were to graph that versus 6 to the x, you'll see that it's different. Okay. So yeah, you have to watch out for order of operations. Okay, then we can do fancy stuff like this also. Like reflect across the x-axis. We played that game before, right? Reflection. And move to the left or right or up or down and all that stuff. So we'll revisit those themes once again. Looks like here the asymptote becomes y equals 1, and we'll see. Right, so here's a combination of stretch, reflect, translate, left, right, up or down. We did a lot of that stuff before. We did a lot of that stuff with trig. So we're just hitting those ideas once again. Okay. Okay, one other base I want you to be familiar with is base E. That seems weird. Okay, what is E? E is approximately 2.71828. It does not seem to make a whole lot of sense now, but you just have to trust me on this. When you get to calculus, you prefer to have base E. You don't like any other base. So in calculus, e to the x is best, believe it or not. Not 2 to the x, not 3 to the x, not even 10 to the x. E to the x is best for some reason. Right now, we can't explain why, but it's there. Well, there's got to be some rhyme or reason to it, because you've even got those buttons on your calculator. So if you have a typical scientific calculator, yeah, here it is. There's e to the x. It's usually above the natural log, ln. Okay, so here's e to the x. If you want to see the actual number e, some of you might have a button that just does e. Otherwise, to trick the calculator into showing you can do e to the first power. So I'm going to go second function, e to the 1. So my calculator turned off. Get it back up here. There we go. E to the first power, 2.7182882. So that's E. It's an irrational number like pi, right? Pi is like 3.1415926, and there's millions and millions of digits after that. It's an irrational number. E is like that also. E is irrational. This is not the end of E. Your calculator only goes out to what? 8 digits, 10 digits, 12 digits, whatever. There's infinitely many more digits. They've calculated E to millions of digits, I'm sure, just like they've calculated pi to millions of digits, roughly 2.71828. Okay, so when you see E to the x, the base is about 2.718. Right now, we don't know why, what's so good about having this weird base, but in calculus, you prefer to have that base. Okay, so e to the x, e to the negative x. Okay, we already know that if you replace x with negative x, that reflects across the y-axis. So this is e to the x. If I reflect across the x-axis, it looks like this. This is e to the negative x. It's decreasing. So e to the x is increasing. E to the negative x is a mirror image, right? If I put a mirror right here, this part here reflects over here, and this part down here reflects down here. So this is e to the x increasing, e to the negative x decreasing. Notice they both still pass through 0, 1. E to the 0 is 1. This would be e to the negative 0, but e to the negative 0 is still e to the 0. That's still 1. Okay. Okay, let's take a look. The domain of f and g, e to the x and e to the negative x, is all real numbers. You can plug in any number that you want to both of these. The domain is all real numbers. You can go as far to the left or as far to the right as you wish for both of them. Range, set of all positive reals. That's like saying 0 to infinity, not counting 0. So the thing that comes out is only positive quantities. Okay, so this graph never touches the x-axis. The x-axis is an asymptote, gets really, 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 really close. Okay? And likewise here, same thing. The range is from 0 to infinity. Okay? You can get really, 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 really close to the x-axis, i.e. y equals 0, but you don't quite touch it. And you can go as far up as you want. Okay. Now you said, do I have to put that on my cheat sheet? It's up to you. You're welcome to put all of this on your formula sheet, but if you put all this in, that's less, less space for other stuff. Okay, y-intercept for both of them, 0, 1. All the exponential functions go through 0, 1. That's because anything to the 0 power is equal to 1. Let's see. The function of e to the x is always increasing. E to the negative x is always decreasing. Okay, we know that. That's going to be true for any base bigger than 1. If the base is bigger than 1, it goes like this. If the base is less than 1, but still positive, its general shape is something like that, always decreasing. Both e to the x and e to the negative x have the x-axis as a horizontal asymptote. So they both have an HA, horizontal asymptote of the x-axis. There's no vertical asymptote. And let's see, for the graph of e to the x goes to infinity as x approaches infinity. E to the x approaches 0 as x approaches negative infinity. So for this graph, if x goes way out here, the y values shoot up like crazy. When x goes way out to the left, the y values approach 0. And a complete reversal for e to the negative x. E to the negative x approaches 0 as x approaches infinity. So when x gets real super big way out here, e to the negative 1,000,000, that's almost 0. And then e to the negative x approaches positive infinity as x approaches negative infinity. So I go, x goes way out here, y goes way out here. So if I plug in negative 1,000,000, I have e to the negative 1,000,000. That's e to the positive 1,000,000. That's super big. So that shoots up to infinity. Okay, then we have these properties of the natural exponential function. These properties are really the same as the ones I just showed you. All this stuff on page, what, 280? They just give you a specific base. So e to the x1 times e to the x2, e to the x1 plus x2, e to the x1 times x2, e to the x1 x2, e to the x1 divided by e to the x2, e to the x1 minus x2. Okay. Sorry if it doesn't look quite focused. I don't have a focus button, believe it or not. I just have to wait for the machine to focus on its own. And if it never wants to do it, then I can't really do anything about it. Okay. Okay, so again, I'm changing the assignment to just 1 and 19 odd. Show you the assignment, do a couple problems, and I'm done for the day. I know it's not completely focused. Get it to focus. That's a little bit better. It's 15, 17, and 19 looks like a matching. So you can see A, B, C, D, and there's I, double I, triple I, IV. Okay. Okay, so number one, sketch the graph showing any horizontal asymptotes. So number one, f of x is 2 to the x plus 1. So first, my version of introduction to exponential functions. Exponential function looks like f of x equals a to the x power. A is a constant, x is a variable. We only want the base to be positive. There's some strange things that happens when a is negative. So we're not going to deal with it. And a is not equal to 1. We don't let a be 1. 1 to the x is the same as 1. That's too cheap. So we won't use that. So these are called exponential functions. There's a whole bunch of exponential functions. 2 to the x, 3 to the x, e to the x. Again, e is about 2.718. 10 to the x, half to the x, 1/3 to the x, and so on. Okay. Again, you probably want to start getting comfortable with your exponential button. It's paired with ln. Here's e to the x, ln. Other type of calculator. ln, sometimes it just says ln, not ln x. And above it is almost always e to the x. So you can see that there. Try to raise this up and focus it, but maybe it's not letting me. Yeah, maybe not. Anyway, that says e to the x there. This is ln for natural log. It's not in as an in. It's ln for natural log. Okay, so maybe I'll just do a couple of graphs and that's about it. So 2 to the x plus 1. First I graph 2 to the x. So I made a table from -3 to 3. There's nothing special about -3 to 3. That it includes 0, positive, and negative. So I guess that's kind of quote unquote fair. Okay, plug in 0, get 1. 2 to the 0 is 1. Plug in 1. 2 to the 1, 2. Plug in 2. 2 squared, 4. Plug in 3. 2 cubed, 8. 2 to the -1 means 1/2, 1/2. 2 to the -2 means 1/2 squared, 1/4. And likewise, this one's 1/8. Okay, so review the rules of negative exponents. So here's quickly what it looks like. 0, 1, so the green, let's see. I'm sorry, and the green is 2 to the x plus 1. Look at the red, 2 to the x. 0, 1, 1, 2, 2, 4, 3, 8, -1, 1/2, -2, 1/4, -3, 1/8. Okay, so it looks something like that. And as we know, when I do +1 like that, the whole graph just shifts up 1 unit. So 2 to the x plus 1, all I did was just take 0, 1, right? That's easy. Move it up to 0, 2. And keep everything else pretty much the same. So like this was what, 1, 2. Move it up 1, so it's 1, 3. Plug in 1, you get 3, right? Okay, so I just try the same basic shape. So the green is the graph of what I'm looking for, 2 to the x plus 1. I started off with 2 to the x, the red one. Okay. All right, I was just going to do one more and then stop. -4 to the x. Number 3, -4 to the x. So first, let me consider +4 to the x. Okay, we already said exponential functions all have the same basic general shape. So, you don't really have to plot that many points. I got real lazy and just did -1, 0, and 1. A 0, 1 on this side, 1 on this side. Okay, so I plug in 0. Oh, sorry. I'm looking at 4 to the x first. 4 to the 0, 1. 4 to the 1, 4. 4 to the -1. 4 to the -1 means 1 over 4 to the 1, or 1/4. Okay, 0, 1, 1/4, -1, 1/4. Just like that. 4 to the x. And when I put a negative in front of the whole thing, that is simply just going to be a reflection across the x-axis. So here's the mirror image, right? Pretend this is a mirror. So from here, it bounces down to here. So here's -4 to the x. This is the point 0, 1. This must be 0, -1. And double check, plug in 0. -4 to the 0 is -1. So there it is, looks something like that. Okay. And folks, that's pretty much it for today. That was all I was going to do. We have plenty of time for only 3 sections, even though we have a holiday. So again, we're aiming for the next test to be when? Friday the 19th. Right? And after that, we just have one more test and a final exam. So we're getting near the end, folks. Hang in there a little bit longer. Give it your finishing kick, so to speak, if you have such a thing. Gear it up. We only have about a month to go. Okay, so I'll stop there. Let me check the chat and see if anybody has any questions. Otherwise, we can adjourn for today. Okay, so let me see. I don't see anything in the chat. Okay. Any questions, please?
So like reflections are basically like on number 3, like the point 1, 4 just goes to 1, -4.
Correct.
Okay, thank you.
Welcome. And same for anything else like that. Yeah, somewhere there was a 1, 4, and 1, -4 ends up down there, right? All right, any other questions, please? All right, I don't see or hear anything, so that's it for today, folks. All right, have a good day, and we'll see everybody next time.
Thank
Bye,
you.
everyone. Thank you.